Hi, my name is John Mathai. I'm a master's student at the University of Illinois studying under Dr. Hans Stein. Today we'll be presenting our data on an experiment conducted in 2013 to determine an estimation for the requirement for standardized ileal digestible lysine in 25 to 50 kilogram growing gilts. We'll start off with an outline as usual. First, we'll go over an introduction to the background behind the experiment, and once we've established that, we'll move into the objectives of our experiment. We will then discuss the lysine titration experiment itself, and following that, we'll discuss the conclusions that we came to as a result of the experiment. And finally, I'll leave you with some take-home messages. As you may know, lysine is typically the first limiting amino acid in most swine diets. This is particularly true when discussing corn-soybean meal diets that are common in North American formulations. Because of this, and because lysine is almost used entirely in the body for protein accretion, with the exception of a small percentage of lysine used for carnitine synthesis, most ideal protein theories express the requirements for other amino acids as a ratio to lysine. Therefore, to determine the requirement for other amino acids in terms of an ideal protein ratio, meaning a ratio to lysine, the requirement for lysine must first be determined in the particular population of pigs in question. Determining the lysine requirement of a population of pigs can be a practical means to determine the requirements for all other amino acids. Because of the nature of any ideal protein ratio with lysine as the first limiting amino acid, the remaining requirements can simply be back-calculated using their empirically determined lysine requirement. One of the most commonly utilized methods for determining amino acid requirements in pigs is an amino acid titration experiment. What these experiments entail is the use of diets with increasing levels of amino acid in question, while all other amino acids are provided at or above the requirement. In principle, we should see that the diet which optimized various growth parameters reflects the amino acid requirement for the animal. There are two schools of thought on how to formulate diets for lysine titration experiments. One would be to use what are called synthetic or purified diets, and the other would be to use more practical, commercially representative diets. The major difference between these two diets is the way in which the amino acids are provided to the animal. In synthetic diets, the amino acids are typically included in the purified crystalline amino acid form, while in practical diets, they are included as complete proteins in typical feed ingredients. In terms of lysine titration studies, practical diets are relatively easy to formulate, because in a typical corn-soybean meal diet, lysine is the first limiting amino acid, and various studies over the years have confirmed this. So the objective of our experiment was to determine the lysine requirement of 25 to 50 kilogram growing gilts, utilizing commercially representative corn-soybean meal diets. To do this, we completed a growth performance study over 33 days, using 70 gilts with an average initial body weight of 24.54 kilograms. The pigs were of the G Performer sire line and the Fertilis 25 dam line of PIC. The pigs were housed 2 per pen and were allowed ad libitum feed and water intake. The experiment was set up as a randomized complete block design, with 5 treatments and 7 replications per diet. There were 5 corn-soybean meal-based diets. The NRC 2012 requirement for 25 to 50 kilogram growing pigs is an SID lysine of 0.98%. Using that as a guideline, we formulated our diets. Diet 1 had an SID lysine level of 0.80%, Diet 2 an SID lysine level of 0.93%, Diet 3 an SID lysine level of 1.06%, Diet 4 an SID lysine level of 1.19%, Diet 5 an SID lysine of 1.32%. As mentioned earlier, the diets did not include any sources of synthetic amino acids. As such, the diets were identical with the exception of an increasing concentration of soybean meal at the expense of corn in order to increase the level of standardized ileal digestible lysine, as you can see here. We analyzed the data from this experiment using the univariate and mixed procedures of SAS, with a fixed effective diet and a random effective block. We determined our treatment means using the LS means function. Broken line and quadratic regression were utilized to help determine requirements and were performed using that nonlinear procedure of SAS. So we'll jump right into the results. We'll first look at average daily feed intake. On the y-axis, we have the average daily feed intake in grams, and on the x-axis, we have our levels of SID lysine in the diets. We see that we have no significant linear or quadratic effects here at an alpha of 0.05. Therefore, we cannot use the average daily feed intake as a means to determine the requirement. However, when we look at the average daily gain, we see that we do not necessarily have a significant linear effect, particularly due to the drop in average daily gain in the final diet, but we do have a significant quadratic effect, which seems to top out at 1.19% SID lysine. So, because we have significant quadratic effect, we can apply a quadratic model to these data. In our case, we used a curvilinear plateau model and used the calculated plateau point as our estimate of the requirement that optimized average daily gain. In the case of these data, we see that the estimated requirement for optimizing average daily gain is 1.08% SID lysine. So if we look at another performance characteristic, the gain-to-feed ratio, we see the opposite of what we saw in the average daily gain, in that we have a significant linear effect, but not a significant quadratic effect. So because we do not have a significant quadratic effect, we cannot apply a quadratic model, such as the curvilinear plateau model we used earlier. However, we can use another linear model. In this case, we used a broken line model in which we determined the breakpoint, the beginning of the plateau, as the estimated requirement for the SID lysine to optimize gain-to-feed. In the case of these data, we see that the estimated requirement for optimizing gain-to-feed is 1.10% SID lysine. What these regression analyses leave us with are two different but very similar values for optimizing average daily gain and gain-to-feed, and that by combining these two values, we conclude that the optimum requirement for growth in 25 to 50 kilogram gilts is 1.09% SID lysine. As we said earlier, the take-home message is the optimum requirement for growth in 25 to 50 kilogram growing gilts is 1.09% SID lysine. However, it should be noted that this value is greater than the recommendation of the NRC for barrows and gilts of the same size, that is 25 to 50 kilogram gilts, at an estimated 0.98% SID lysine. There are probably a couple reasons for that. The NRC requirements are for barrows and gilts, and we know that barrows and gilts do not have the same requirements. Gilts eat less daily and therefore require higher concentrations of amino acids in the diet. Additionally, the NRC agglomerates data from various experiments that involve animals of different genetics, health statuses, and even on different diets. That being said, the values determined in this experiment are in agreement with published values using gilts fed similar diets under commercial conditions. With that, I would like to acknowledge the sponsors of this study, Evonik and Ajinomoto. And thank you for listening to this podcast. If you enjoyed this presentation and would like to hear more, please visit our website at nutrition.ansi.illinois.edu. Thank you for your attention.